Hello, hello, hello. Welcome back, guys. Today is, what is it? Tuesday, 16th of June. And today we got our final session going through the OCR MEI paper 3 with that tricky little comprehension section. I know that that's the one that's not very well catered for in terms of existing videos. And I've had a lot of comments and people reaching out. Hello, hello. Lots of comments and people reaching out, asking for a bit more advice, particularly on that section B, the comprehension bit. So what I think I'm going to do today, do what I do normally, blitz section A, so we kind of get that out the way. But I really want to spend some time. I'll go through a bit slower in this section B, explain what I'm seeing and how I'm kind of piecing it together from the question. So I know before I was kind of just doing it, whereas I think now I want to get a bit more into like how I'm piecing it together, not just what to do. So also feel free to drop things in the comments. You know, I like to respond to it if you've got some other things. How have I been? I've been well. Thank you for asking. We're coming up to the end of exam season now. So I can kind of, at the start of exam season, you could feel me getting real stressed and worked up. But now we're kind of getting to the end. We're seeing the light at the end of the tunnel. It's kind of calming down a bit. But for you, what that means is not getting too relaxed too quickly and making sure you keep that momentum going through Thursday. But it's only 48 hours to freedom, guys. So close. Hello, hello. Right. So that's the goal for today. Let me just pop you guys over here. Let me start my screen share. I'm going to do entire screen so we can see everything. Yeah, when was the last time you seen a full live solve? Not done till it's done. Yeah, 48 hours. 48 hours. And that's why, by the way, I'm going to do a recap tomorrow, a debrief tomorrow, because I know the second, in fact, if I'm still chatting, I shouldn't be sharing. So what I know is like the second you guys are done on Thursday, run for the doors. It's summer holiday time. No one's going to want to come back here and like talk about how it went. That is where you put it all behind you and just like wait till results day. Exactly. So tomorrow I'm going to do my final little debrief and then let you guys head off for freedom. Right. So let's get into it. Right. Let me check that the sizing is okay. Always let me know, by the way, if you can't see very well. You have numerical methods on Friday. What? How are there still exams? Outrageous behavior. Well, okay, you've got a little bit longer. But in which case, well, we're close to the end, though. You can sense it coming. It's just a case of like emptying the tank, getting everything out of the system that you can, get every mark you deserve. So let's get into it. Question 1. Curve for which y is inversely proportional to x. Find the equation of this curve. Are they? Because am I being punked here? That's just y equals 1 over x. You see, I can see how people would totally get in their own heads about this, but like, look where the asymptotes are. Like this approaches the y-axis and it approaches the x-axis, and x is positive, y is positive when x is positive. There's no transformation on that. Oh, sub in the values. Clever, clever, clever. Yes, apologies. So we know, sorry, why is it? Thank you, chat, for stopping me. So, see, I was going to mislead you all. You see, this is what chat is for. Chat is stopping me doing, okay, why was I being stupid there? So what I was doing was I was looking at that and thinking, oh, well, this is just going to be based on a 1 over x curve. What I missed is the fact that it's inversely proportional, and I should have immediately gone down that. Well, if it's inversely proportional to 1 over x, then that means that y is equal to k over x, and you have to find your value of k by plugging in set values. So 2 equals k over 1, so k is equal to 2, so y is just equal to 2 over x. Thank you, chat. Apologies. I would have caught that in the checking, though. I would have caught that in the checking, I think. I hope. See, this is how you know it's close to the end. The wheels start falling off. Focus, Patrick. You've got this. So we got this function on this domain. we've got this other function for all real numbers, f of g of x. Well, that's what happens when I plug g of x into f of x. So f of g of x is just equal to the square root of 25 minus x squared. Cool. B part 1, find the domain of that thing. Well, in order to do that, I need to find the domain of that. What I need, think about g of x, right? In order to have a valid g of x has to be bigger than or equal to 0 to be plugged into f of x. So where is g of x bigger than or equal to 0? Well, that's when 25 minus x squared is bigger than or equal to 0. So that's 5 minus x, 5 plus x. So we know the limiting values are x equals 5 and minus 5. And with any quadratic inequality, I'm going to sketch it. So it does something like that, where that's minus 5, that's 5. And we want this thing to be bigger than or equal to 0. So it's between minus 5 and 5. Because anywhere there, I can plug that in. G of x will be bigger than 0, and that will go in there. Cool. Now find the range of that. Well, I know that the range for g of x, I know that it is less than or equal to 25. That is the range of g of x, which means it is the sort of domain going into here. So that means what's going into f of x will also be, it has to be bigger than 0 in order to go into f of x, and it has to be less than or equal to 25 just by the nature of what the function is. So when I plug those values in, that means f of g of x, when x equals 0 on one end, that will just be 0. And when x is equal, g of x is equal to 25 on the other end, it'll be 5. So that is the full complete range of g of f of x. Sorry, f of g of x. Right, let me drag this across. So we have an infinite series, sorry, an infinite sequence. Give it a definition, find the limit of the sequence. Right, so in the limit of the sequence, a of n plus 1 equals a of m at the limit. In fact, I'll even say it equals L at the limit. So I'm not sure this is the specific technique they want for this exam board, but I have seen it used. So I'm going to use it here. So what that means is that if I plug it, so that means that n plus 1 over n plus 2 I don't think this is what it means. Sorry, no, what I'm talking about is when it's recursive. So when it's based on the previous values. So what I'm going to do instead is do a cheeky rewrite of this. Or I'll say as n tends to infinity, you can say that a of n, because what's going to happen is the 1 will become negligible. So it's going to tend to 1, certainly. If you want another way of thinking about that, and the reason why is because it'll tend towards n over n, which is equal to 1. Because the 1 will become negligible on the bottom. If you want to see this another way, you can rewrite the top as n plus 1 minus 1 all over n plus 1. And then if you separate out the fractions, then clearly it's going to be 1 minus 1 over n plus 1. And as n tends to infinity, this second thing will go to 0, so it will tend towards 1. So that's another way of getting there. Okay. Prove that this is an increasing sequence. I suppose what we're going to do here is I'm going to consider a of n plus 1 minus a of n and show that it's a positive number. So that'll be n plus 1 over n plus 2 minus n over n plus 1. Let's get these to common denominators. So n plus 1 squared all over n plus 1, n plus 2, minus n plus 2 all over n plus 1, n plus 2. Now, this I'm doing intuitively. I think at some point I'm going to have to do a big deep dive on this specific specification. So I'm not sure if there's a very specific technique they want you to use here, but this is what I think works. And we'll find out in the mark scheme if there's something specific that they want. So when we subtract these off, this then, well, the n squareds will cancel, the 2n will just cancel, and you end up just getting 1 over n plus 1, n plus 2. And so the difference, therefore, an plus 1 is bigger than an for all n, because the difference this expression, this difference between successive terms, is bigger than 0 for all positive n. Yeah, that should be positive. So I think that's what they're going for. Okay, back into more familiar territory. So we've got this guy. Now immediately, what am I seeing in this trig? I know in order to solve trig, it needs to be in the form of trig value equals number. So we need to get it all in the same trig value. In this case, I know that cos squared can be turned into sine squared, so that's what I'm going to do. Cos squared is 1 minus sine squared. Exactly. And when we expand this out, we're going to get a quadratic. So if I move this to the right, we'll get 2 sine squared x plus 3 sine x minus 2. Now this is a quadratic. Some people will substitute in here and say 2y squared. In fact, I'll show multiple methods of doing this. I'll do the most direct method first, which will be 2 sine x and sine x. And it'll be plus 2 minus 1. Now, how else could you have done that? Well, let's say, I'll pause it there and say, well, if it had been something like 2y squared plus 3y minus 2, we could have said the target number is 2 times minus 2, which is minus 4. And then the factors of minus 4 that sum to 3 are plus 4 and minus 1. So we could have said 2y squared plus 4y minus 2, and then factorized in pairs. So from the first pair, I can take out a 2y and form a y plus 2. And from the second pair, I can take out a minus 1, and then you're left with the y plus 2. And because those two brackets are the same, I know I'm right, which gets me 2y minus 1, y plus 2. And again, the y is just sine x, so you can plug that back in. I did mine by inspection, by saying that 2 sine squared can only be formed from 2 sine x and sine x. And then the way to get that is to get the plus 4 from 2 plus 2, and then there's a minus 1 to bring it down to 3. So by inspection, if you're comfortable with it, otherwise using a more robust method. But the point is we've now got to the point where 2 sine x equals 1, so sine x is a half. And this is in radians, so I know that's going to be pi over 6. And the reason why I know that is my special triangle, my 1, 2, root 3, where that in there is pi over 3, and that in there is pi over 6. So pi over 6, opposite over adjacent, gives me my half. Now, from the cast diagram, I know I am also looking in the where sine is positive, I will have pi minus this to give me 5 pi over 6. And those are all the solutions to that equation. And then the alternative is that sine x equals minus 2, for which there are no solutions, because sine x can only go as far down as minus 1, which means I have found both solutions. And it says exact, and I have given them in terms of pi, so that's good. Alrighty then, question 5. Now, the real interesting, stick around because the interesting bit's going to be in section B. I'm looking forward to it. All right, so here, implicit differentiation, that will just become 4x. This will become first d second plus second, which is y, d first, which makes that 3. Whenever it's a function of y, I always do d thing dy, dy, dx. So differentiate that with respect to y, and you get 2y, and then multiply by dy dx. 2 differentiates to 0, 0 differentiates to 0. Now we have to make the dy dx the subject of the formula. So 3x plus 2y, lots of dy dx, equals the negative of 4x plus 3y. Excuse me. And I got that just by subtracting these terms across to the other side. So now we've got dy dx, utterly illiterate on my part, apologies, equals the negative of 4x plus 3y all over 3x plus 2y as given. Good. So now, in 5b, so we've got our dy dx. We got to find our stationary points. We know that's when dy dx equals 0. So therefore, the negative of 4x plus 3y all over 3x plus 2y must equal 0. Now, this clearly happens. We can multiply both sides by -1 to clear that. And the way this is going to happen is when 4x plus 3y is equal to 0. So 3y is minus 4x. So y is minus 4/3 x. So this condition has to be true in order to have a stationary point. So now we have to find which points on this curve also lie on this line. So this becomes points of intersection. And the way to do that between a curve and a line is to substitute the line into the curve and then solve for x. So yeah, 4 marks. This kind of justifies it. So we have 2x squared plus 3x into minus 4/3 x plus y squared plus 2 equals 0. And we're going to get a quadratic from this. So that's going to be minus 4x squared. This is going to be plus 16 over 9x squared plus 2 equals 0. Now, 16 over 9, so this is minus 2. Now, don't be a hero. I'm just going to use the calculator because I can. So that's minus 2/9. So minus 2/9 x squared plus 2 equals 0, which means that 2 is equal to 2/9 x squared. The 2's cancel, so 9 is equal to x squared. X is equal to plus minus 3. And we have to plug that in here. So when x equals 3, y equals minus 4. And when x equals minus 3, y is equal to 4. So it looks like the coordinates are 3 and minus 4 and minus 3, 4. I can check that quite easily when we get round to that. So here we've got cooling, the rate of decrease in temperature, which is dt dt. So d big T over d small t. And that is going to be, so it's proportional to that. So that's going to be equal to k times that thing. That is me writing down the differential equation for 2 marks. So now I think we have to solve this. So rate of change of temperature is k into t minus 20. A lot of people would be tempted to bring the k down, but my advice is to always leave anything. Only move the things that absolutely have to be moved. So big T has to be moved to the left. So you do that, but the k does not need to move, so don't move it. So you bring the dt up and you're integrating that. Now this thing here will just become ln of t minus 20. And this thing here will become kt plus c. At this point, I'm going to say when t equals 0, big T is equal to 90. So that means that ln of 70 is equal to c, because little t will equal 0. So in other words, ln of t minus 20 equals kt plus ln 70. And I'm going to bring all the logs on one side and combine them in order to get rid of the log. So using your log laws, when you subtract the logs, you divide the argument. And then we can say by taking the exponential both sides, that would be e to the kt. So t minus 20 equals 70 e to the kt. And t is going to be equal to 20 plus 70 e to the kt. And we are told, in fact, what I should have done is, I should have done this at the start, to be honest. But we could have found k by saying from here, if I go back to here, so apologies to the flow of this question, but we know that it is decreasing at a rate of 4.9, so it's minus 4.9 is when the big T is equal to 90. So k is equal to minus 4.9 over 70, which is minus 0.07. And it's negative because it's decreasing. So I just used, I needed way more room than they've given me. I don't know if I did this in a very inefficient pathway, but I'm gonna just scroll my little way across to here and plug in the facts. So t is equal to 20 plus 70 e to the minus 0.07 t. And we want to determine how long it takes to cool to 40. So 40 equals 20 plus 70 e to the minus 0.07 t. So 20 is equal to 70 e to the minus 0.07 t. 2/7 is e to the minus 0.07 t. Take natural log of both sides and divide by 0.07. Yeah, they really are. They are inefficient with their space. Like it's, I mean, columns, doing what I'm doing here and working in columns, I think is just the way to go. So I'll tell them what I'm doing. So there's a rule of thumb. Anything that you type into a calculator, you should also write down so that you can pick up method marks in case you type the wrong buttons. 2/7 all over minus 0.07. So I'm getting 17.9. And what are the units? It's minutes. Okay. Right, so question 7 now. Ugh. Okay, so we're trying to find the binomial expansion of this thing. She gets these first 3 terms. She draws the true graph. The first 2 terms, then the first 3 terms using software. Explain why this is bigger than this. Because 6 to the x over 8 is bigger than or equal to 0 for all x, because the power is even. Or in other words, I can write this as, just for a bit of fun, I can write that as x squared over 2 all cubed. And we can see that because x squared is bigger than, it must be positive for all x. It means that the whole thing, so if you're cubing a positive number, you get a positive number. So this thing is definitely positive for all x, but the reason why is because it's being raised to an even power. So in other words, x to the n is bigger than 0 for all even n. I'm just writing just like belt and braces everything you could probably write here. So because 6 is even, this thing is positive, so you're adding a positive number to the thing, so it just is bigger, right? Okay. So B, explain why the graphs suggest that the student has made a mistake. I would say it's because the graphs diverge. But in fairness, using the binomial expansion, it should only be valid because we're using the year 2 method here. We're using the method for fractional and negative indices. We know this is only valid for certain values of x anyway. And in this case, it's only going to be valid when the magnitude... when the magnitude of negative x cubed is less than 1. So it should only be valid between -1 and 1 anyway. But I'll just say it's 1 mark, so I'm just going to say the graphs diverge, and if they wanted something else, I'll let them explain it. That doesn't feel like actual math here. Because they are pretty good between 1 and -1, apart from at 1 itself. All right, it's words. I'm not going to judge myself for not getting the words. So C, find the first 4 terms. Let's do this. That's no room at all. All right, so it's 1 minus x cubed to the half. Now that is going to be 1 plus a half, thing at the back, plus a half, 1 minus a half, or a half minus 1, all over 2 factorial times thing at the back squared. They want the first 4 terms. So then it's going to be a half minus 1, a half minus 2, all over 3 factorial, thing at the back, cubed. Nice and systematic, no execution errors. 1 minus a half x cubed. Now this is a half times minus a half, all over 2. It is minus an eighth. Oh, it's minus an eighth. Minus an eighth x to the 6. And I'm wondering if I can use some exam technique now and go back, now that I know it should have been minus, and they've explained to me that it's bigger. Okay, I'm going to go back and change that answer. But in the meantime, 0.5 times minus 0.5 times minus 1.5 all over 6 is 1/16. But then this is, so this coefficient would be positive, but now I'm cubing a negative number, so this is negative overall. So it's negative a 16th x to the 9. Now, guys, here's what I'm thinking. I'm going to revisit this because they've made me think, all right, well, this curve is above this thing, but has made a mistake because the true curve, I'm not going to say the graphs diverge. What I'm going to say here And look how I think it's cool that like me demonstrating how I'm rethinking this now. What we see here is the true curve lies below the y equals 1 minus x cubed over 2 curve. So as we've added the new term on, we've moved the entire curve even more positive, further away from the true curve. So what should have happened is, by adding more terms on, I should have got closer. So I'll say adding the third term of x cubed over 8 took us further away from the true curve, not closer. So in other words, the true curve is this one on the bottom. Our first attempt got us this one in the middle. By adding new terms on, I was supposed to get closer, but instead I got further away. I got more positive when I should have got more negative towards the real one. So I think that's what they were going for. And you'll notice I did that by sort of question geography, like kind of understanding that the parts are going to feed into each other. And by finding the true value, I then sort of went back and reevaluated what was supposed to happen. So you're totally allowed to do that, and I recommend you do that in the real thing. So state the values for which it's valid. It's valid for when the magnitude of the thing at the back is less than 1, which means that the modulus of x is less than 1 in this case. So E, we have, so sketch the curve. Well, that's quite simple in that it's just the original curve with the y values multiplied by 2.5. So that should be 2.5 minus 2. Sorry, that's 3. So where it's 2 should end up being 5, basically. 3 times 2.5 is 7.5. So that should end up there. 0 times 2 is just 0. That gradient should still be flat. So I'm gonna something like that. Okay. Sketch that curve. Cool. The end of a bus shelter is modeled by the area between the curve I just drew, 900 meters. Calculate using your answer to parts. Okay. So what I'm going to do here for F is it should be the integral from minus 0.75 to 0.75. It should be the integral of 2.5 root of 1 minus x cubed dx. That's what it should be. Now, using your answer to part C, so in other words, it should be the integral from minus 0.75 to 0.75 of 2.5 into the expression I found, which is 1 minus a half x cubed minus an eighth x6 minus a 16th x to the 9, if memory serves me correct. 8th x6, 16x9, yes. Okay. So in other words, it is the integral of minus 0.75 to 0.75 of, I'm going to do exact fractions here, 5 over 2, 2.5 times a half, so it's minus 5 over 4x cubed, minus 5 over 16x to the 6, minus 5 over 32x to the 9. So now we got to perform that integral. So that is going to become 5 over 2x raise the power to 4 and divide by 4 and get 5 over 16x to the 4. Raise the power to 7 and divide by 7 and we get 5 over 112x to the 7. Raise the power to 10, divide by 10. Yeah, so 5 divided by 32 and then divided by 10. So it's 1 over 64 x to the 10. And this is going to be between 0.75 and minus 0.75. Notice how I go slowly to make sure I don't make any execution errors. Okay. In fact, let me show you at this point. Let me check that my calculator is still good to go. Good. So I'm going to bring this in. No. Stop doing silliness. Go away. So what I'm going to do, run matrix. I'm just going to do 0.75. Plug it in, and then I'm going to say 5 over 2 answer minus 5 over 16 answer to the 4 minus 5 over 112 answer to the 7. Now, realistically, if this was actually my exam, I might go like term by term. But if I know that space is at a premium, and if I'm feeling confident from my position, I'm going to just plug that in as is. So 1.7692844046 minus, and then I'm going to do the same thing with minus 0.75. In fact, hold on a minute. I'm wondering if I go up, if I change this to minus 0.75, boom. All right, it's scrolled through and replaced everything below with the new value. So that is specific to the CG50. I need to get an emulator for the ClassWiz one and get better at, that's one of my summer projects, is get better at the calculators and how to demonstrate calculator skills. But this is one way. If you have the CG50, if you don't have the CG50, you would just retype it and plug it in. You can also use the answer using the integral function. Yes, you can. And I had a trouble with that. So I know on the ClassWiz one, like the original ClassWiz before they ruined it with the CW, the 991EX has a very clear integral button on it, which is super helpful. I know it must exist in here somewhere. I just haven't found out how to do it yet. But you're right. You can integrate it directly and just confirm you get the definite correct answer. But now I'm going to do 1.7692844046 plus 1.96879.775. You get 3.74 to 3 significant figures. Math, then scroll to end and you should see it. Where's math? Oh, math. There's math. Thank you very much, sir. I shall definitely get on that in the checking phase. And this is why we have chat, because chat knows more than me. Love it. All right, so that's an approximation. Okay, so here now we have question 8. We have a curve and its inverse where h is given. X-axis at b, find an expression for the inverse of x. Okay. So we know that y equals x cubed minus 8 is the original. And in order to work out the inverse, we swap around the x and the y, and we make y the subject. So x plus 8 is equal to y cubed, and y is equal to the cube root of x plus 8. So that is your inverse. Nice. For B, determine the coordinates of A, B, C, and D. Well, A and B are given by y equals x cubed minus 8 for A and B. When x equals 0, y equals minus 8. When y equals 0, 0 equals x cubed minus 8. So 8 equals x cubed, and x is equal to 2. So therefore, that means that A is 0 minus 8, and B is equal to 2, 0. Now, y equals the cube root of x plus 8 for actually, okay, I'm going to do this next part 2 ways. But for this one, this is certainly true for C and D. So if you don't know the trick, you can just do this as usual. When x is equal to 0, y is equal to the cube root of 8, which is equal to 2. When y is equal to 0, the cube root of x plus 8 is equal to 0. So x plus 8 is equal to 0. So x is equal to minus 8. So A is 0 minus 8. B is 2, 0. C is 0, 2. And D is minus 8, 0. Now, the trick to avoid having to do this math at the end is to recognize that a function and its inverse are mirror images of each other through the line y equals x. In other words, all you have to do is to flip around the x and the y. So 0 minus 8 flips around into minus 8, 0, and 2, 0 flips around into 0, 2. So that's just a quicker way of getting to the points on the inverse. So C, determine the equation of the perpendicular bisector of AB. Okay, well, in order to do that, so we know, let me remind myself, so A is equal to that, and B is equal to 2, 0. So first thing I want to do is find the midpoint. So we take the average x, not divide by 0, divide by 2, there are 2 numbers, no, what am I doing? Over 2. And then the average y is going to be that. So it's going to be 1 minus 4 is the midpoint. Now the gradient between A and B is the change in y. So it's 0 minus minus 8 all over 2 minus 0. So it's 8 over 2, which is 4, which means that the perpendicular gradient is going to be minus 1 over 4. So we know the gradient of the line. We know the coordinates of a point that the line goes through. So y plus 4 is minus a quarter x minus 1. And it wants it in the form y equals mx plus c. So y plus 4 is minus a quarter x plus a quarter. So y is minus a quarter x. Now, minus 4 plus a quarter is minus 15 over 4, and that is your perpendicular bisector. D. These 3 points lie on a circle. Determine the equation of the circle. Interesting. Okay, so the point here. Now, again, let's think about question geography. So I have just been asked to find the perpendicular bisector of AB. Now, what I know is that the perpendicular bisector of any chord must go through the center of the circle. So what I can do is to similarly find the perpendicular bisector of any other chord, find where those 2 lines intersect, and that will tell me the center of the circle. So I'm going to do it for ease. I'm going to do it for BC now. So B was 2, 0, C was 0, 2. The midpoint of those guys is just going to be, I was almost not going to write it out, but it's just going to be 1, 1. The gradient of BC, So change in one, so it's 2 minus 0 all over 0 minus 2. Well, it's just equal to minus 1. Therefore, the perpendicular is minus 1 over that is just 1. So therefore, y minus 1 is equal to x minus 1. So it's just y equals x. And in fact, I should have known that. I should have known that they reflect through the sort of y equals x line. So the point here that I'm making is, if I now know that the center lies on this line, and I know that the center lies on this line, and I think they wanted me to, oh no, continue, maybe they didn't. But the point is I can find the center by equating these two lines. So to find the center, I say that x is equal to minus a quarter x minus 15 over 4. So let's multiply both sides by 4. 5x is equal to minus 15, x is equal to minus 3, and y is equal to minus 3. So I've now found the coordinates of the center. So the center is at minus 3, minus 3. So I know the center now. And now I need to find the radius. So I can just find the distance between that point and any point I want. So in this case, B. So B is at 2, 0. So the radius squared. So the change in y is 5 squared. The change in x is 5. The change in y is 3. 25 plus 9, which is 34. So therefore, it's just x plus 3 squared and y plus 3 squared equals 34. That was fun. And now we get to the main event. All right, guys. So first thing I'm going to do is I'm going to read the insert. I want you to pay attention to what happens as I read the insert, because I am not going to necessarily... let's have this conversation. I am not necessarily going to understand everything that's happening in the insert. So what you want to do is to just strip out from the insert wherever you can understand some core syllabus idea. Like, I won't understand all of this, but it's like, oh, but that's tangent, that's normal, that's where they intersect. I can kind of get that. Or just something like that. So you'll see me simplify, just pinpointing where the syllabus material is. From there, I'm just going to, and it's a lot of show that, right, in section B. So from there, I'm just going to piece it together, piece by piece. So first thing I'll do, okay, so here's my insert. Do you recommend reading the insert first in full or only coming back to it when you need it? I'm going to read it first in full so I know what themes there are in the insert. All right. So let's move this across so I can get the insert in full and start sharing so you can actually see what I'm doing. Okay, so for small angles. So immediately I'm thinking about small angle approximation is happening. Yes. Okay, so we're talking about small angle approximations. So we show sine x and y equals x. And then we've moved this across to form an expression. Presumably, you can set it equal to 0. Inspecting the graphs suggests it's good. Yeah, but okay. Calculating sine of x, cool. So we've had our small angle. Not always possible in the past. This approximation is only reasonable close to 0. Oh, so can we introduce higher order? Okay. Okay, so they've taken the max and the first 0 of the sine curve and forced a quadratic to fit that. And then the difference between them, so this is clearly very good when the difference is small, suggests it's good everywhere really up to pi. Yeah. Calculating percentage errors for selected values shows that the percentage errors are quite high. Oh, okay. But of course they would be because you have to divide by the true value, which is very close to 0. Okay. So again, I'm just telling myself the story of what's been happening. So we're doing approximations using a straight line close to 0. We're doing approximations using a forced quadratic, which is better for a better range of values, although there might be something to do with that they ask me. Better approximation. 7th century. God damn. Go you. That's outrageously good for the 7th century. All right. So it is symmetrical about pi over 2. It does go through the points it needs to. Radians were not in use until the 18th century. So we did it in degrees. Interesting. The percentage error is less than 2% throughout the entire interval. And apparently you can do that, and now we're done. Okay, so this is all about approximations. So we've got 3 types of approximation. This is all about how good a fit it is for the sin x curve. That's all I've taken away from that. So what I can do now is I can summarize. Just at a high level, this is about approximations to sin x. So we have the linear approximation when x is close to 0. We have a forced quadratic, which is good between 0 and pi. And then we have the better forced quadratic from that random Indian genius from the 7th century. And there's also this idea of percentage errors, which is the difference over the actual times 100. Okay. That's it. I've just reduced that entire thing down to those points, which are easily understood using syllabus material. I don't know what specifically they're going to ask, but I do know that from this point forward, the questions are going to be given in the answer booklet. So I can have the answer booklet here giving me the questions, and then the insert to look through here on the left. So I can kind of get rid of the question paper at this point, because otherwise you have like all the sheets of paper on your desk at once. Okay, so now show that this thing has the same gradient. Now I didn't need to read now that's the other thing, by the way. It's entirely possible to do some of these questions about the insert without having read the insert. So this idea here of showing that they have the same gradient, I don't need to read the insert for that. I can just use my math skills, which does make it somewhat easier. So maybe if you're intimidated, you can go across to the answer booklet and see what you can answer without the insert. But to me, this is going to feel approachable because of the way I edited down the insert. Because of the way that I kind of just boiled it down to like the key summary points. Okay, so getting back into this. For y equals x, we have dy dx is equal to 1. For y equals sin x, dy dx is equal to cos x. When x equals 0, cos of 0 equals 1. Therefore, it's the same. 10. Figure C22 indicates that this curve has a stationary point so the difference curve. So this guy has a stationary point near x equals 3. Verify that the x coordinate is between these two values. This is going to be change of sign, I think. Huh. So it's a stationary point. So what I'm going to do, first of all, okay, so I'm going to get the dy dx of that. So that is going to be first d second plus second d first minus cos x. So it's minus 4x all over pi squared plus 4 over pi minus 4x over pi squared. I'll call that 4 pi over pi squared. So in other words, it's 4 pi minus 8x all over pi squared. And then not forgetting about my minus cos x. Now, what I imagine is I'm going to say when x is equal to 2.6, and we're going to do the same thing that we did before. So 2.6 equals, we're going to consider 4 pi minus 8 answer all over pi squared minus, oh, hold on a minute. We're about to find out whether I'm in radians. I think we might be because I'm seeing rad. That looks good. Dy dx is equal to 0.0226-ish. When x equals 2.7, the gradient is equal to, now I'm just going to go up here, change it to 2.7, follow that through, boom, it's become negative. Change in sign and interval. Therefore, dy dx equals 0 in the interval. So therefore, stationary point at interval. So what I did there, I saw that it's between these two. That immediately made me think of the change in sign. But then where I went with that is, well, in order to have a change of sign, I need to have the equation equaling 0 having a root in that interval. So I went, what is supposed to equal 0 there? Ah, it's a stationary point, so the gradient is supposed to equal 0 there, which is why I found the gradient function, which is supposed to equal 0. We're trying to find the root of the gradient function, and we show that there's a change of sign in that interval, and therefore that there's a turning point in that interval. Show that this stationary is a maximum. I'm going to do that. Oh, you have no room. Why do you have no room? Boo. All right, so I'm going to differentiate again. So the first part will just differentiate to 0. We'll have a minus 8 over pi squared. Minus cos differentiates to plus sine. And we know that, let me just check what 3 pi over 4 is. Yes. So what we know is that 3 pi over 4 is less than 2.7, is less than the root, is less than 2.8, is less than pi. So in other words, we know that this stationary point is between 3 pi over 2, 3 pi over 4 and pi. Oh, it's certainly between pi over 2 and pi, actually. That's what I should have done. So in other words, I'm thinking about what area of the cast diagram we are. Oh, that doesn't help. Maybe this isn't how I'm supposed to. Oh no, that's stupid of me. All right, so I don't think we are meant to do this by the second derivative. I think we've shown the gradient on either side of the stationary point. So we know it's going from, the other thing we know is that it's going from positive to 0. So at 2.6 and at 2.7, it's going from positive and then to negative. So therefore the gradient is decreasing and therefore it's a maximum point. So that's what I'm thinking. So we've shown the gradient on either side of the stationary point. So it was going from positive gradient to 0 to negative gradient. Therefore, the gradient is decreasing and it's a maximum point. Okay. Yeah, that makes much more sense. And that's why it could be done from where we, like, using the work we'd already done. All right, so here at 11, show that for the angle 45 degrees, the formula blah gives the same approximation for the sine of the angle in blah. Blah. Okay, well, gives the same approximation for the sine of the angle in the formula, that. Okay, so in degrees, so sine of 45 degrees is approximately equal to 4 times 45 into 180 minus 45. So I'm just doing what I'm told at this point. I can't believe they had to do this without a calculator. My God, this must have taken all day. So 4 times 45 times 180 minus 45, which is 135, but I'm not going to risk any mental math errors. Minus 45 into 180 minus 45. That's 12 over 17. And sine of, now 45 degrees is pi over 4 radians. So 16 times pi over 4 times pi minus pi over 4 all over 5 pi squared minus 4 into pi over 4 into pi minus pi over 4. Well, that is equal to 4 pi into 3/4 pi all over 5 pi squared, cancels, minus pi into 3/4 pi, cancels, 3 pi squared all over 5 pi squared, minus 3 pi squared, lies, total lies. That is 3/4 pi squared, multiply top and bottom by 4. Equals 12 over 17. So they both give you 12 over 17, which is good. Okay. 12a, show that this thing is true. All right. So what I'm going to do here is to use the, see, I'm barely using the insert at all. So that is going to be sine x cos pi over 2 plus cos x sine pi over 2. Actually, hold on a minute. And that is using the formula given to you in the formula book for the expansion of, in fact, let me see if I can find you where that is. So that is here, the trigonometric identities for compound angle. So sine of a plus b form. So then coming back to here, oh no, insert. Yeah. We're really focused here on the question. So this cos of pi over 2 is 0. Sine pi is 1. So in other words, it's just equal to cos x. Not a problem. Oh, let me zoom out for a bit. In fact, what's happening here? Hence show that that gives that. I think what that means, so cos x is equal to sine, oh no, sorry, I shouldn't be doing it. Oh no, it is hence. No, that's b. So I should be doing that down there. Boo. No, I'm going to start b up here. I just want the question. So equals sine of x plus pi over 2. What I'm going to have to do is to plug x plus sine over 2 into the sine x approximation. So it's 16 x plus pi over 2 pi minus vx plus pi over 2 all over 5 pi squared minus 4 x plus pi over 2 into pi minus x plus pi over 2. So it's just a straight substitution. Now, how am I going to simplify you? Well, where am I going to get to? I'm going to get to here. Let me just slowly chip away at this. So 16 x plus pi over 2 pi minus x minus pi over 2, which is just pi over 2 minus x. Now that's a difference of 2 squares, which is fun. 5 pi squared minus 4 x plus pi over 2, and this is going to be the same pi over 2 minus x. Well, that's going to be 16 into, now I can rearrange this in my head and call that pi over 2 plus x. So that will be difference of 2 squares. So pi squared over 4 minus x squared all over 5 pi squared minus 4 into pi squared over 4 minus x squared. So let's multiply that through now. So that will become 4 pi squared minus 16x squared all over 5 pi squared minus pi squared plus 4x squared, which is 4 pi squared minus 16x squared all over 4 pi squared plus 4x squared. Divide top and bottom by 4 and pray I didn't make a mistake. Nailed it. Boom. Okay, that's how that... Is that it? Oh, that can't be it. We barely used the insert. Didn't use that. What are they talking about? Hold on a minute. No. Why are they... No. What are they doing talking about all this percentage error stuff and then not making me do something with percentage error? What you playing at? You pay silly. Do better. Oh, man. I was hoping that would be more interesting. No offense. Sorry. Sorry if you found that difficult. No. Well, that was nearly interesting. I do think they were the 23 and 24 were harder. So let me recap. Did I need the insert for any of this? I didn't need the insert for that. I didn't need the insert for that. I didn't need the insert for that. Oh my god, I basically didn't need the insert. So you're quite right. Maybe you can get away with not reading the insert. I don't recommend it. I very much recommend reading the insert so you kind of know what's happening. But that was interesting. I've not seen that. Okay. So what's my takeaway here? So the insert still guided my thought process for what I was kind of looking for. But then it was just a lot of it's with section B, it's a lot of just do what you're told. Where did I have to do some cleverness? This is why some people jump straight into the questions. Honestly, I get that at this point. I still think it was helpful for me to read the insert, so I kind of knew it kind of loosened the jam jar. Rather, if I'd seen these things kind of blind, I might be like, why is this happening? This no cleverness required. This required a little bit of cleverness to tie in the syllabus material of finding a root in the interval, and in order to do that, finding an equation set to 0. And a little bit of cleverness here to show it was a max. This required not much cleverness, just a lot of carefulness. And understanding that here I was going to need to use pi over 4. Here, this didn't require cleverness, just carefulness again. And that was it. That was actually that was a remarkably good, I think, section B in the grand scheme of things. I've seen ones like the 23 and 24 ones required a lot more thought about how to do things. So I think we got away with it. But in the meantime, I am going to get into the checking phase. First thing on my way up, I'm going to make sure I have answers to every part of every question. It looks like I have not missed anything out. Good. All right, so let's get into the checking phase. Checking super important for seeing if you've made any execution errors. So here, what I can do is plug in some various points. Y equals, so 2 over 1 is 2, 2 over 2 is 1. This works. Write down an expression for that. What I'm going to do is I'm just going to check it to make sure it all tracks. So for instance, I'll just use that value. Why not? So let me do f of g of that. So first I'm going to do 25 minus answer squared. And then I'm going to do root of that. Oop, apologies. Shift that. So root of that is 4.95. If I go back to 12 over 17, and I plug that into my expression, root of 25 minus answer squared. Same thing, so therefore mine is good. That is a valid expression. Find the domain of it. So when x is between these values, g of x is positive, which it needs to be good. Find the range of f of g of x. Well, we know that the g of x goes between 0 to validate going into the f, up to 25, which is the maximum for g, which means that f of x is limited to a maximum of 5. This tracks, this is good. Find the limit of this sequence. Well, I mean, we can just plug this in because we can just do, 9 times 10 to the stupid, all over 9 times 10 to the stupid, and then plus 1. It's 1. Good. So it does 10 to 1. Prove that this is an increasing series. I did that because I proved that the difference between successive terms was positive. And maybe I can just check to make sure I didn't make a mistake there. So let's use, so what I'm going to do is I'm going to plug in, I don't know, 5.714. And I'm going to do answer plus 1 all over answer plus 2. And I'm going to subtract off from that answer all over answer plus 1. And I'm going to subtract off from that what I think the difference is. So if that equals this, then that minus this should equal clean 0. And clean 0 is what I'm always looking for when checking my work. Answer plus 2. Clean 0, that's correct. So that is the difference between successive terms. And for positive n, this thing is always positive. So the difference is positive, so it's increasing. All right, so for exact solutions for this is going to be nice and simple. Let's plug them in. So pi over 6, we're still in radians, so let me plug that in to here. So it's going to be 2 cos of the answer squared minus 3 sine of the answer, clean 0. Let's make this 5 pi over 6, still a clean 0. So those two are correct solutions. Are they the only solutions? Well, you get a quadratic, 2 solutions for sine x into pi. I found those. The other gave me sine x is minus 2, which has no solutions, so that should be correct. Show that this thing, I did show that. Find the coordinates of the stationary points. All I'm going to do here is to plug in my values and make sure they give me a 0 for dy dx and that they do truly lie on the curve. So here, if I have, no, stop it. If I have minus 3 minus 4, no, stop it, stop it, stop it, stop it, stop it. Help, make it stop. I'm always going to be playing, tag with that. Right, so here, let me just confirm 4x would be 12. So in both of these cases, yes, the gradient will very simply be 0. Because 4 times that is 12, 3 times that is minus 12, cancels. 4 times that minus 12, 3 times that 12, those cancel. Good. So I know that the gradient is 0 at those. What I'm going to want to do is to plug them in and show that they actually fit the curve. So 2 times, well, 2 into 3 squared plus 3 into 3 into minus 4 plus 16 plus 2. Good. That is on the curve. 2 into 9 and 3 into minus 3 into 4 plus 4 squared plus 2. Good, clean 0. Right, so these do lie on the curve and they do have a gradient of 0. This is correct. So I found the coordinates of the stationary point. So here, write down the differential equation. I did. Does my differential equation fit these parameters? So this is my finalized form. When t equals 0, well, actually, sorry, this is my finalized form. When t equals 0, big T equals 90. Good. When t equals 0, let me just check. So when I differentiate this guy, I know I'm going to get minus, so 70 times 0.07 is 4.9. So it will be minus 4.9 e to the stuff. And when t equals 0, e to the stuff equals 1. So I'll get minus 4.9, which is correct. So this is the correct differential equation. And when I plug in 17.9, let's see what I get. So 20 plus 70 e to the minus 0.07 times 17.9 minutes. I should get close to 40. Yeah, 40 degrees. Good. Here for 7. There's something along those lines. It's the fact that I'm adding something that's positive, so it has to be bigger. It has to get bigger. Now here, it's made a mistake because adding the next term has got me further away from the true graph, not closer. Yes, I would recommend doing the questions first and then doing a checking stage because you want to make sure, let's have that conversation. So checking technique, you do want to make sure you've answered all the questions first, because what you don't want is to spend time checking, which ends up being wasted time because you've got them right, and then you've left entire questions blank that you don't get to or that you get to in a rushed state. So in terms of maximizing your percentage chance of using your minutes to get marks, going from nothing on the paper to something on the paper massively increases your mark percentage. Whereas checking your work, there's a smaller chance of gaining marks from that effort because chances are you did it right the first time. So in terms of playing the probabilities, yes, step 1, put everything on the page. Then step 2, check to try and pick up some extra marks. Because what you don't want is something that happened to me in my actual A-level. I went through the entire paper. I then started checking from the front. I was like, oh, this is going so well. Look at me, I'm getting all these marks. Get to the question towards the end of the paper, realize I've accidentally missed out an entire part D of the question, which was worth 7 marks because I just didn't see it. So the first thing you do, make sure you've got everything down, then go checking your work. Alternatively, if you are not confident in what you just did, and if it's easily checked, you can kind of do it on the spot. So trig, plug the values back in, show you get clean 0. That was really easy to do. You can do that if you're not feeling confident about the work you just did. But the benefit of going through, putting everything down on paper, and then coming back to it is if you do make a mistake, it's much easier to spot it and correct it with fresh eyes, because chances are you can just do it again and it's going to work, right? So that's why I recommend doing it the way I'm doing it here. I'm so curious what you did for the first 2 papers. I'm very curious to see what other strats are available. But I'm happy with what I answered here. It's a wordy one, so I don't really care. Okay, checking this is going to be quite simple. I'm going to plug in just a small value of x and confirm that these are basically the same thing. So I'm going to 0.000548, for instance. I'm going to do the root of 1 minus answer cubed. No. I'm going to do the square root of 1 minus the answer cubed. And from this, I'm going to subtract off this entire approximation. So minus 1 plus a half answer cubed plus answer to the 6/8 plus answer to the 9/16. Gives me an incredibly small number. This is good. This is the correct approximation. State the set of values for which it's valid. X magnitude of x less than 1. Sketch this curve. I did. All right, so now let's see if I can find out. So you've been very helpful pointing out how to do this thing. You said, oh yeah, definitely do not do the checking stage while doing the questions. No, answers first, then checking. Make sure you, yeah. Because again, let's think about that. The percentage of you spending your minute picking up a mark is much higher in laying down a fresh answer than it is in checking. So it's just better use of the minutes that you have available. Maximizing marks per minute. There's an on average lower amount of marks per minute available from checking your work because of your percentage chance of getting it right the first time. So here, let me see if I can do, you said math. And then you scroll. Ah, look at it. Integrate. Yes. Beautiful. Thank you so much, sir. This is why we have people in the chat. So we're going to integrate. And we're going to need to do it an approximation for the area using the model that I calculated in C. So no, stop it, no, stop it. Fighting with the tech. All right, so it's going to be 2.5 into 1 minus a half x cubed minus x to the 6 all over 8 minus x to the 9 all over 16. And that is going to be between minus 0.75 and 0.75. Please. Yes. Okay. Good. Now 8. Find an expression for the inverse. This is a fun check. I like this check because what you do is you just plug in. In fact, let's just keep this value. Let's plug that into. So answer cubed minus 8 gives me a y value. And if I plug that y value into my inverse, I should get back to my original. So the cube root of that thing plus 8 is my original. So that is the true expression of my inverse function. Determine the coordinates of A, B, C, and D. Well, that is fairly standard fare. You just plug in. Well, is it even worth it? Yeah, it's fine. So 0 cubed minus 8. No, I'm just getting a bit silly. But so 0 minus 8, 100%. 2, 0, 100%. And those flip. They flip around like these are just correct. What is a bit, so determine the coordinates, yes. Determine the equation of the perpendicular bisector of AB. Do I have any issues with this whatsoever? So 1 minus 4, that is correct. Gradient was 4, now it's minus a quarter. Is this minus a quarter? Does it go through that point? Yes. So I'm happy with that being the perpendicular bisector. Where it gets more interesting is now what I can do is because I use that perpendicular bisector to work out the circle, I feel much more confident about the validity of my circle equation about that perpendicular bisector if the circle is valid. So if the circle is valid, then you'd think that the perpendicular bisector would have to be as well. So what I'm going to do at this point is make sure all of the points that I had, A, B, C, and D, do lie on this circle. So add 3 to both, square them, I should get 34. So I'm going to do 0 plus 3 squared plus minus 8 plus 3 squared. Good, gets me 34. So 0, 8, let's change it to 2, 0. Get 34, great. Let's change it to There we go. 0, 2. Great. And let's change it to minus 8, 0. Nice. So all of those points lie on the line, so I feel good about that. Okay. So then we get into the section B of it all, where I think the checking for section B is actually remarkably easy, because it's so many show that's like this, I've shown that they both have 1. Verify that this, I did. There's a change of sign in the interval. Show that it's a maximum. Well, I did. It's going from positive to 0 to negative. Show that this gives me the same. Well, they both give me 12 over 17, which are the same. Show that this is true. Well, I just did. And show that this is true. Well, I just did. So the checking, while the actual questions themselves are harder in section B, the checking is really easy. Like, you tend to know with certainty whether you got it right or wrong. Whoop, sorry. No, keep you guys off there. I'm going to move you over. Stop that. Whoop. So, wait, what am I doing? Guys, I haven't marked it. What am I doing thinking I'm done? No, I'll give some debrief on that. So hopefully you guys have picked up. So that checking technique is important. It's definitely important you do it at the end again so that you're making good use of the time. Also, by the way, if you have limited time left and you want to be strategic about what to check, it's best to do it. So some of that wasn't really worth the payoff, right, for the amount of work I put in, but some of it really was. So things like plugging the trig back in, plugging some algebra back in, that doesn't take a lot of time and it gives you a lot of certainty. Whereas just redoing the problem doesn't really make you more certain you got it right. So some of the questions will be easier to check than others, and I recommend you lean into those if you need to prioritize. If you get something that isn't a clean 0, or if you see something is wrong, it then lets you know that that is where you need to go in, find a correction, pick up an extra mark or 2. All right, so now finally, let's mark all this up. So scrolling to the top, got the mark scheme, especially for some of the wordy ones. I want to see if I got all the way over the line, because I'm confident on my equations, but I'm not confident with my words, because I do not words goodly. So, all right, so this y equals 2 over x. Thank you, chat, for saving me from my own stupidity. Yep, there's that. That's good. That's good. 1. Huh. Well, it's funny because I even rewrote this, but okay. So less is being taken away. I wonder if is an alternative. Is there an alternative? Yeah, here we go. I did this one. I did alternative 2. So I took the difference, and the difference is bigger than 0. What did they do? Does this make sense? I don't know if that makes sense, but this certainly makes sense. So you're taking off a smaller value, so you're getting bigger, and like you approach one in the long term, but the reason why you're not at one is because you're taking something off, but that thing you're taking off is getting smaller and smaller, so you get closer and closer to 1, and so it's increasing. I'm not gonna lie, I really like my method. Question 4. Yep, pi over 6, 5 pi over 6. 5a, you get there. 3 minus 4, minus 3 and 4. Yep, that's a, nice and simple. 7.9 minutes, perfection. Bigger than 0, great. The expansion with 2 terms is better approximation than the one with 3 terms, but it should be the other way around. Boom! And that's how you do it. That's how you play the exam game. Because I completely didn't get that until I'd done C. Then I went back and got there. That is how you play the game. I'm proud I got that one. So that, yep. Goes through that. Right shape. Yep. Because it goes flat there, which is important. And you get 3.74. Do I need a unit? No! Ah! No! Yeah. Okay, that I'm so annoyed at. I got must include units. Must include units. God damn it, guys. I'm normally so good at that. I know. Because it's an area, length are in meters. It did say it's right. This was a model, so I was supposed to say what the things mean. God damn it. All right. So that's important. In modeling, always think about units to avoid that pain. Ugh. I'm just going to set fire to something. I'm so mad. Right. So this is cube root of 8, x plus 8. That is so stupid. It's not even fun, that. Oh, no. What are you doing being in A-level, giving mixed numbers? Absolute troglodytes. No. Improper fractions. Oh, interesting. Yes. So the intersection of any two of the perpendicular bisectors, you get the median. Yeah. That's what I did. Okay. So then both of these just give you 1. Both of these give you, oh no, I didn't do this one. Where's 10? 10. There you are. Yep, and yep, gradient is 0 between that, and it's going from exactly positive to 0 to negative, so it's a maximum. Good. Here, both of them give you 12 over 17. Oh, boo, come off it. Come on, do some actual math on that. There you go. That's what I like to see. And then here, you just plug it in, rearrange, keep it good. Oh, man, I was so close, guys. I was so close. So in conclusion, if you pay attention to your units, you can get full marks. All right. Now, hopefully, you guys find that useful. So the thing that messes people up in this paper is going to be section B. Section B, if you're getting really lost in the insert, my recommendation is not to panic and just see what you can do blindly from the questions, because a lot of the time you can do it independent of the insert. If it helps, you can summarize the insert to get a sense of what types of ideas are about to come up, so it kind of loosens the jam jar a bit. Simplify it, bring it back to core syllabus, taking the gradient, setting the gradient to 0 if it's a turning point, understanding how to take a gradient from the derivative, how to form a tangent, how to form a normal. These sorts of core ideas still apply even to weird questions. So a lot of the times it's about identifying the skill from the syllabus they want you to apply and just carefully applying it to the problem as given. And because it's a show that, you know with certainty whether you've got it right. So that's my advice for handling that. And then the advice for the other stuff is, as usual, just be accurate and then use some good checking so that you know your calculations are accurate. You might still lose mark on the wordy bits, like I missed out the units, but at least you feel a better degree of certainty that like you're on the right side of a grade boundary, for instance. If in doubt, if you're completely lost, just try and demonstrate any skill that you have from the syllabus to justify the effort you put into learning the syllabus. So if you're like, all right, I have no idea what section B is on about, but there's something here about a gradient, and I know how to find a gradient by taking the derivative. I'm just going to show you I know how to do that. These kinds of games help you pick up extra method marks, right? So those are all the things you can do to help yourself. Now, with that, I think we are done with our A-level streams. I'm going to do a checkup tomorrow at 4:30 for a bit of a debrief. Ooh, question. For the question where you did the perpendicular bisector thing, you wouldn't even have thought of that. So that is part of the syllabus, knowing that the perpendicular bisectors of any two chords will intersect. So the syllabus point that you know is that the perpendicular bisector of any chord goes through the center of the circle. That's known. You don't need to go through all of your circle theorems, but there are certain ones like angle in a semicircle are 90 degrees, tangent meets radius at 90 degrees, and that the perpendicular bisector of any chord goes through the center. Those are the ones that you need for A-level. So you're right that there are alternative methods there. What they did there was they kind of just did simultaneous equations. They said they plugged in. So for 2 unknowns, you need 2 equations. For 3 unknowns, you need 3 equations. So they will have had to have plugged in the coordinates of 3 points into the equation x minus a squared plus y minus b squared equals r squared. That gives you 3 equations with 3 unknowns, and you can solve that simultaneously. If in doubt or if low on time, if you've got the CG50, you can just plug those into the CG50 and it can solve for you. That's probably what I would have done if I'd forgotten that. Yes, they're all. In fact, I didn't even get the primary method. Let me go back to that. Let me go back to that just to clarify that for you. So here, the primary method on that one, if you probably remember, that was question 8. I do remember. So their primary method was exactly, they solved, yeah, they plugged in all the coordinates and then solved simultaneously for A, B, and R. But also, actually, they're all R squared. So when you subtract them, the R squared goes away. You solve simultaneously 2 of them for A and B. And once you then know the center, you can just find the distance from that center point to any of those points, and that becomes the radius. So yes, any valid method should get you all the marks. So just do whatever you can. I've had papers in the past where I just fully missed the intended solution path. And I was saying the whole way through, like, this is so wrong. This is so not what we're supposed to do. But I used a skill and it got me the right answer, so I got all the marks. So just demonstrate anything you've got from the syllabus and you should be fine. So hopefully that helps. Glad you guys pressured me to do this MEI, because that's actually really good fun, this paper. I will see you guys tomorrow at 4:30 for us to go through, actually, maybe not 4:30, because then I won't get to eat. Maybe it'll be more of a 4:45 and like a shorter debrief rather than a full hour. But I'll definitely get some debrief with you guys, especially for any of you doing your discrete in your further math today, or decision math, you might call it. So just a chance for anyone to pop in, debrief about what's gone on, ask any final questions about the math tomorrow. And then you're free, guys. And then, well, you're free. I'm not free. Now that I'm straight onto the ESAT cycle. I might take a... No, I'm not going to take a week off. Let's be real about that. You'll be free. So good luck, guys. Work hard. Pick up every mark you deserve. Get yourself through to the other side so you can feel really good, because you don't want to be kicking yourself going out into a summer. Launch yourself into the summer feeling celebratory and like you've done your best work, that you're looking forward to results. And I will definitely be checking in with you guys on August 13th just to see how everyone feels about, how it's all gone down. But right, in the meantime, I'm going to leave you to it, and I'll see you tomorrow. All the best, guys. Good luck. Take care.